Hello. We will go over some problems from this 16.2. This section is quite long, therefore I will break it into two parts. I will do even numbers. I noticed from my lecture videos 16.2a, I didn't do any problems from this book. I only went over the exercise set. I mean the examples. So I think I will do even problems from number 1 to number 16. And then in the next supplemental video, after you watch the lecture video for 16.2b, then we do more supplemental problems from there. Okay, let's start. Keep in mind that this section, when we do this part, a lot of them just substitution, but you need to know what it means. For example, ds, as we have learned before, is the magnitude of r prime t dt. Okay, from chapter 13 or 14, right? So suppose I need to do number 2. We have integral over curve C of xy ds, where the C is parameterized by t squared 2t t from 0 to 1. So r prime t is 2t comma 2. The magnitude will be 2 times square root of t squared plus 1. Okay? Implicitly, later on, our ds will be our ds, which is magnitude of r prime t dt. This will be 2 square root of t squared plus 1 dt. Okay? Now, and then if we go to the integral, that will be integral from 0 to 1. X will be t squared. The y will be 2t. ds will be 2 square root of t squared plus 1 dt. That's the setup. Okay? How do we do it from here? I think we have issue with the t squared plus 1, huh? Let's substitute that ugly guy. U equals to t squared plus 1. So du will be 2t dt. 2t dt. That's our du, huh? Okay, this will be our du. And our t squared will be substituted by u minus 1 then. The limit of integration, u at 0 is equal to 1, u at 1 equals to 2. So my integral now becomes integral from 1 to 2. Okay, u minus 1, that's for the t squared. 2t dt becomes du. Okay, and then 2u to the power of 1 half. Which is equal to, let me go to the right, this is equal to 2 integral from 1 to 2 u to the power of 3 half minus u to the power of 1 half du. Okay, that's 2 times 2/5 u to the 5 halves minus 3 halves. 2/3, not 3 halves. 2/3 of u to the power of 3 halves from 1 to 2. That's 2 times 2/5 4 radical 2 minus 2/3 2 radical 2 minus 2/5 minus 2/3. Okay. What will this be? The first one will be 2 times 2 radical 2. Hold on. I try to do factorization here. 2. Yeah. Not a good idea. Let me just do it properly. I tried to do a shortcut, but I get confused myself. So this is 2 bracket 8 radical 2 over 5 minus 4 radical 2 over 3 minus 6 minus 10, that's negative 4, plus 4 over 15. So 24 minus 20, that's 4. 4 radical 2 over 15 plus 4 over 15. So this is actually 8 over 15 radical 2 plus 1. Okay, I hope I do it right, but it's that's basically that way. Okay, that's basically that way. That's for number 2. Let's go on with number 4. Move this down so that I can have more space. Number 4. Number 4. Integral over curve C of x sine y ds, lowercase s, not uppercase, where C is the line segment from 0,3 to 4,6. So we parameterize that by 4t 3 plus 3t, where the t is from 0 to 1. You may wonder, Thomas, how do you do that so fast? The initial point is 0, 3. Okay, so the initial point is 0, 3. Okay, and then the direction factor is the difference. 4 for the x component, 3 for the y component. So that's 4t. If you remind yourself, it's basically the initial point, which is initial position factor 0, 3 plus the direction factor 4, 3, right? That's how we get that one. Okay, and then the t is from 0 to 1. Therefore, r prime t will be 4, 3, whose magnitude is just constant 5. Okay, so when I do the substitution, it will be integral from 0 to 1. X will be 4t sine 3 plus 3t 5 dt. Okay, I can factor the 20 out. Integral from 0 to 1 of t sine 3 plus 3t dt. From here, I will do integration by parts. So this is 20 times negative 1/3 cosine 3 plus 3t plus 19 sine 3 plus 3t from 0 to 1. So when t is 1, there will be negative 1/3 cosine 4 plus 19 sine 4 minus, when t equals to 0, I get negative 1/3 cosine 3 plus 19 sine 3. I don't really like this, honestly. I don't really like this. But I guess that's the furthest I can go, huh? So that's 1/3 cosine 3 minus cosine 4 plus 1/9 of sine 4 minus sine 3, like that. 20/3 of cosine 3 minus cosine 4 plus 20/9 sine 4 over minus sine 3. That's too ugly though. Honestly, that's too ugly. You know what? I just realized I make a silly mistake. This not 4 but 6. When I substitute the t by 1, it becomes 6 here. Instead of 4, it should be 6. Okay. Oh yeah, I forgot the t here. So this is when t equals to 1, t equals to 0. This will be 0. This is not this. Not that. Cosine 3, so not like this. Not like this. Okay, so it seems like I can simplify it a bit further though. Hold on. Let me check my work. I forgot that t and it messed up the whole thing. Okay, you know what? I think I can do the common factor 20/9. So -3 cosine 6 plus sine 6 minus sine 3. Yeah. Okay. Sorry. I forgot that t and messed up the whole thing. Let me rearrange them first, make it look nicer. Okay, now I think it's better. Okay, let's see number 6. Number 6, find that integral over curve C of e to the x dx. Not ds, be very careful. Where C is the arc of curve x equals to y cubed from -1, -1 to 1, 1. If we parameterize that, then when y equals to t, then it will be t cubed comma t, right? For with t from -1 to 1. So it means x as a function of t is t cubed, dx therefore is 3t squared dt. Notice we only need the x, right? So this becomes integral from -1 to 1 e to the t cubed times 3t squared dt. But if we do substitution u equals to t cubed, our du is 3t squared dt. Right, and then u at -1 is 1, -1, u at 1 is 1. So this integral now becomes integral from -1 to 1 e to the e to the x again. What am I doing? Actually, I can use x instead of u. You know, okay, e to the u du. That's e to the u from -1 to 1. That's e minus e to the -1. Okay. I think number 6 is on the easier side. It's just We were expecting that to be a ds, but this is instead it's a dx. Okay, number 18, number 8. Let me give myself some space. Number 8, I have integral over curve C of x squared dx plus y squared dy. If you think about this, this is actually integral over curve C of x squared y squared dot dx dy. Now, notice that this is our dr. If we parameterize the C, okay? So let's parameterize the C first. C is the arc of the circle with radius 2 from 2, 0 to 0, 2. Oh, it consists of two parts. So this is the C1 followed by the line segment from 0, 2 to 4, 3. This is our C2. This is 4, 3. I see. Okay, so it seems like we need to do the C1 is parameterized by R1t, that is 2 cosine t 2 sine t, where the t is from 0 to pi over 2. Okay, and then for C2, call that R2S. Don't use S. Maybe T1, T2 then. I may get confused. Yeah, I will just use S, but remember this S here is not the arc length thingy. S will be 0, 2 as the starting point, and I need to go to 4, 3. So this will be 4 T. Okay, where the T will be from the S, not T. From, yeah, I think I just use T then. But I hope you don't confuse that T in the first curve and the T in the second curve. Okay. Okay, now then, so R prime, R1 prime T will be negative 2 sine T, 2 cosine T, and R2 prime T will be 4, 1. Now notice that C, if I rewrite that, C is basically C1 union C2, right? Of x squared y squared dot dr t. That is equal to integral over the first curve of x squared y squared dot drt, dr1t now, plus integral over the second curve of x squared y squared dot dr2t. Okay, let me go on further. In C1, it is parameterized by t from 0 to pi over 2. The x squared is 4 cosine squared t. The y squared is 4 sine squared t dot negative 2 sine t, 2 cosine t dt. That's for the first curve. Okay, as for the second curve, we have integral from 0 to 1 of x squared, that's 16t squared. The y squared is 2 plus t being squared dot 4, 1 dt. So you see it's just substitution, right? Okay, for x squared y squared in C1, This is the x, this is the y, this is r prime, r1 prime, x squared, y squared, r1 prime, the limits of the integration, right? And as for the second path, this is the x squared for t, right? The y squared from 0 to 1, r2 prime dt. Now let's put things together. This is integral from 0 to pi over 2 negative 8 cosine squared t sine t plus 8 sine squared t cosine t dt plus integral from 0 to 1 of 64t squared plus 2 plus t being squared dt. I will simplify that further, of course, but let's do this for now. Integral from 0 to pi over 2. I can factor 4 sine t cosine t, can I? And then I have 2 sine t minus 2 cosine t. Now, why don't I just factor the 8 out? You know what? I will just integrate it one by one later on. So, what will this be? This is negative 8 over 3 cosine becomes sine of cosine cube t plus 8 over 3 sine cube t. That's from 0 to pi over 2. Okay. Plus 64 over 3 plus 2 plus t cubed over 3 from 0 to 1. When t is pi over 2, this is 0 minus 8 over 3 again. Oh, okay. Plus when, oh, this is already done. Plus 64 over 3 plus at 1, that will be 9 minus at 0, that's 8 over 3. Am I? I feel like, but I think I'm okay though. Yeah, I think I'm okay. So that cancels. This will be 56 over 3. 9 plus 56 over 3. 56 divided by 3. 54 is what? 18. That's 27. 2 over 3. Is that right? This will be what? Divided by 3. That's 1, 8, 54. 2/3, right? Okay, that's for this question number 8. Next, let's do number 10. Number 10, we have integral over curve C of x, y, z squared ds. It's a ds, where the C is line segment from -1, 5, 0. Oh, this is three-dimensional, to 1, 6, 4. So the RT, when we parameterize that, will start from -150 plus t times the difference, that's 214. Of course, R prime t, therefore, equals to 214, right? But I prefer to write the RT in a more complete way. RT will be 2t minus 1, t plus 5, and then 4t. Why? Because I need to substitute that here. Integral from 0 to 1. Let me write it here. The t is from 0 to 1. The x is 2t minus 1. The y is t plus 5. The c squared is 16t squared. The ds is, I need to find the magnitude, r prime t in magnitude. That will be 16 plus 4 plus 1, that's square root of 21. Okay, anything after that, just computation, right? That will be 16 square root of 21, integral from 0 to 1. That's 2t to the fourth. 10 minus 1, 9. It's 9t cubed minus plus 9t cubed. Yeah, minus 5t squared dt. So 16 square root of 21 times 2/5 plus 9/4 minus 5/3. Dang, how to do that? The LCD is 60, huh? The LCD is 60. Let me try. Let me relearn, repractice my pre-algebra. I do LCD 60, so that will be 2 times 12 plus 9 times 15 minus 5 times 20. Reduced by 4. That will be 4 square root of 21 over 15, but this will be 24 plus 135 minus 135, that's 59. So 59 times 4 is 236 square root of 21 over 15. That's for number 10. Okay, let's go on. Let me give myself some space. Number 12. I really do all even numbers. Yeah, it's practice, it's practice. Okay, so we have number 12. We have integral over curve x squared plus y squared plus c squared ds, where the curve is parameterized by t cosine 2t sine 2t, where the t is from 0 to 2 pi. Okay. It actually looks like a spiral, huh? Yeah, it looks like a spiral. Yeah, it looks like a spiral. So r prime t will be 1, -2 sine 2t, 2 cosine 2t, whose magnitude will be square root of 1 plus 4 sine squared 2t plus 4 cosine squared 2t. Oh, I thought it would be ugly, but it turns out it's not. That's 1 plus 4. That's square root of 5. Okay, nice. Okay, so the integral now will be from 0 to 2 pi. X squared becomes t squared plus y squared becomes cosine squared 2t plus sine squared 2t. Oh, that becomes 1, huh? Square root of 5 dt. So this is integral from 0 to 2 pi t squared plus 1 square root of 5 dt. I will factor the square root of 5 out, right? And then 1/3 t cubed plus t from 0 to 2 pi. Well, I will just replace that by 2 pi then. So, oh, I'm sorry, square root of 5. Square root of 5 times 1/3 8 pi cubed plus 2 pi. I can factor the 2, I can factor the pi. So 2 pi radical 3, I'm sorry, radical 5 over 3 times, if I factor 2 pi out, that will be 4 pi squared plus 3. I see, right? That's for number 12. Number 14. I hope at this point you already have a feeling on how to work on these kind of questions. Okay, integral over curve C, number 14 of, I will write that as a dot product, y c x dot dx dy dc, which will be our r prime, right? R prime dt. Okay, so where c is parameterized by rt, square root of t, t and t squared. The t is from 0 to 4. So r prime t will be 1/2 t to the negative 1/2 1 2t. Okay, so now our integral will be from 0 to 4. The y will be t, the c will be t squared, the x will be t to the 1/2 dot 1/2 t to the negative 1/2 1 2t dt. By the way, this guy here is not r prime t per se, but it is r prime t dt. It is a differential, right? So it should equal to a differential. We can rewrite this as dx dt, dy dt, dc dt, that's for the r prime t, okay, times dt, right? Okay. I purposely write in t to the negative power so that when I do the dot product, maybe it's easier to compute. So I get 1/2 t to the 1/2 plus t squared plus 2t to the 3/2 dt. Now you know what I mean, right? So the first integral is 1/2 times 2/3 t to the 3/2 plus 1/3 t cubed plus 2 times 2/5 t to the 5/2 from 0 to 4. So that's 1/3 4 to the 3/2 plus 1/3 4 cubed plus 4/5 4 to the 5/2. So 1/3 times 8 plus 1/3 times 64 plus, hey, is that 2 to the 5th, 32. 64, 128 over 5. That's 72 over 3 plus 128 over 5. 72 over 3 is what? 24. Plus, that's also 24. 25 and 3/5.6. So that's 49.6. Leave it as fraction if it is not a nice decimal. Okay, that's for number 14. The last one. Oh wait, you know what? I just realized. I make a mistake. I copied something wrong. It's not 0. It's not 0. It's not 0. So please do some adjustment then. Okay. I need to change this. I need to change this. You know what? Let me do it. Let me do it. So change this to be 1. Change this to be 1. Change this to be 1. Good thing I don't think it's too hard to do because it's subtracting by 1. Minus 1/3 plus 1/3 plus 4/5. What will that be? So 2/3 plus 4/5 is 10, 12, 22 over 15. Okay, so whatever this is, minus 22 over 15. What will that be? 24. That's 49. I'm gonna write it first. 24 plus 25 3/5 minus 1 7/15. Do you know how to do this kind of subtracting mixed number? Do you remember? Multiply by 3, so that would be 48 2 over 15. Okay, I'm tired, honestly, sorry. Do too many integration today in one day. Okay, number 16, the last one. Integral of a curve C of, let me rewrite it right away, y plus z, comma, x plus z, comma, x plus y, dot, dx, dy, dz, where the C consists of two paths. C1 is line segment from, call that R1T, from 0, 0, 0 to 1, 0, 1. So that will be T, 0, T then, huh? Where the T is from 0 to 1. Okay, and then the C2 will be from that 1, 0, 1 to 0, 1, 2, 0, 1, 2. The T again from 0 to 1. Okay, wow, then there will be a lot of substitution, huh? So R1 prime T will be 101. R2 prime T will be negative 1, 1, 1. Okay, so the integral over C of that y plus c, x plus z, x plus y dot dr, drt is now can be written as the sum of two such integral over C1 plus integral over C2. Okay, and then I plugged it in, 0 to 1, y plus c is for the first path, that's t, x plus c is 2t, x plus y is t dot 1, 0, 1 dt plus integral from 0 to 1 x plus c. That's I'm sorry, y plus c. Y plus c is 1 plus 2t. X plus c, that's 2. X plus y is 1 dot negative 1 1 1 dt. Integral from 0 to 1, there will be t plus 0 plus t dt plus integral from 0 to 1 of negative 1 minus 2t plus 2 plus 1 dt. They happen to have the same interval of integration, so actually I can just put them together, right? So that's integral 0 to 1 t plus t. You know what? Let me just put them together first. Hold on. Integral from 0 to 1 of 2t dt plus integral from 0 to 1 of negative 2t plus 2 dt. Don't you think that's really nice? Integral from 0 to 1 of 2 dt. That's 2 times the length. Wow, it's not too bad, huh? Okay, that's for this section.